بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. In this session, we will present a complete design problem that is similar to the one that you will do in the design problem, where we will design a complete circuit and then model it and simulate it using Verilog. This circuit is called adder-subtractor circuits. This is the circuit. This circuit will have two main inputs, A and B. Both are 16-bit long. And we have SA and SB. Each one of them is 1 bit. These represent a sign, two signs. And then the result is Y. Y is actually SAA plus SBB. So this is a sign in front of A, and this is a sign in front of B, and this is an add operation. So if this is 0 and this is 0, so we'll have A plus B, because both are positive. If this is 0, this is 1, we'll have A minus B, because the sign in front of B is negative. If this is 1 and this is 0, so we'll have minus A plus B. If both are negative, SA and SB, so it means 1 and 1, so we'll have minus A minus B. Also, we'll have an option to detect the overflow. So overflow can happen. If overflow happens, we need to detect that. This is what we require to do. This is the problem definition. And then we'll start by drawing the complete block diagram for the circuit, and we call this top-down design. We'll start from the complete diagram of the circuit, complete block diagram, and then we dig into the details of each module in the circuit. And this is the complete block diagram of the circuit. What we are computing actually is, as we said, SA A plus SBB. Okay, let me name this W and name this S. So ultimately we need to add W to S, so we need an adder, 16-bit adder. This is 16-bit, this is 16-bit. Let us assume this is W, this is S. But what is W? W, if SA is 1, so W will be the 2's complement of A. So that's why we have the 2's complement of A here. This is if SA is 1. If it's A is 0, we need to add A as is. So that's why we have this multiplexer. Same thing for the B. If SB is 1, we need to compute the 2's complement of B. So S will be the 2's complement of B. If SB is 0, S will be B as is. Also, we need a module to detect the overflow. The flow, it depends on SA itself, the sign, and the sign of A, and SB, and the sign of B. So SA, SB, sign of A, sign of B. Also, the sign of the end result Y. If you remember in chapter 1, we said, for overflow to happen, this two signs must be, the sign of W must be the same as sign of S, so both can be either negative or positive. And at the same time, the sign of Y should be different than these two signs. So this is positive, this must be negative. These two signs are negative, this must be positive. And we'll see the details when we build this module. Now we need to build these modules. We'll start with number 1, the 2's complement. Then we'll build the adder. Then we'll build the multiplexer. Then we will build this overflow checker. In the top level design, we need to start with the block diagram, and you will do that same thing in your design problem. You will draw the block diagram for the whole circuit. And you will divide your circuit into sub-modules. Then we'll build these modules. Let us now start with the 2's complement. two's complement, we need to have a circuit that computes the two's complement of 16 bits input. So we have 2 to the power 16 cases, which is more than 65,000 cases, which is impossible to do it using a two's table. A simple way to do it is to build something called 1-bit comp that takes only 1 bit of X and compute the complement. Okay, how to do that? Let us take an example. Assume that this is our input. It must be 16 bit. I will not draw the whole 16 bits. Now, to compute the two's complement for this input, I have to split this input in 2 portions. For the first part here, the output will be the same as the input. After that, the output will be the opposite of the input. This depends on the first non-zero here. After this first non-zero appears, after that, the output will be the opposite of the input. Before that, the output will be the same as the input. So now for this 1-bit comp to compute the correct Y, it needs to know if the first non-zero already happened or not. And this information can be conveyed as an input here. We call it DI. So for this module, if DI is 0, that means the first non-zero did not appear yet. In this case, the Y will be equal to the X. If DI is 1, that means the first non-zero already appeared, then the Y will be the opposite of X. Okay? And each module will convey the same information to the module next to it. Okay? So let's see how to build this module. We'll do this module very simple. Assembly, as we said, Y will depend on DI and XI. So let us focus now on the gate module. Assume this is the gate module. We have XJ. We need to compute YJ. And this is, we name it DI. And this is DO. Okay. Well, let me now compute the YI. We said YJ, sorry, will depend on the DI. If DI is 0, YJ will be XJ. If DI is 1, YJ will be XJ bar. So if DI is 0, so DI bar will have XJ. Or if DI is 1, we will have XJ bar. And it is clear that it is the XOR between DI and XJ. Okay, this is for the DI. And we will build a truth table for that, but let us see it first. For the DO will depend on the DI. If DI is 1, DO will be 1. So for the DO, if DI is 1, this will be 1. Or if XI is 1, DO will be 1. So if it's already known from the previous stages that the first non-zero already appeared, that means DO will be 1. And the same information will be conveyed to the next stage. Or if this is 1, that means the first non-zero appeared here. So this is an OR operation, and it can be just directly DO equal DI or XI or XJ, sorry. Okay, and we can see the complete truth table for that. Let us see it. This is a complete truth table. This is the DI, XI. You have 4 different combinations, and this is YI. This is DO. As we said, YI, if DI is 0, that means the first non-zero did not appear yet, so the YI will be the same as the XI. If it is 1, that means the first non-zero already appeared, so the YI will be the opposite of XI. If you see, now this YI is actually the XOR between DI and XI, as we did before. For the DO, if the DI is 1, DO must be 1. Or if the XI is 1, DO will be 1, otherwise be 0. And this is the OR operation between the DI and XI. Let us now start writing the Verilog module for this circuit. Okay, now let us write a Verilog module for that. This is a module for 1-bit COM. And this is the circuit. Say module, 1-bit COM. We have 2 inputs, 2 outputs. Input XI, input DI, output YI, output DO. As we said, the DO is the XOR between the inputs. So this is XOR, sorry. So the YI is XOR. And the DO is the OR. This is the OR in the 2 inputs. Okay, let us now try to run this using Quartus. I'll copy this. This code here, Control C. Actually, we'll not do. Before we do that, let us see the complete circuit. Okay, sorry for that. So this is now 1-bit module, and this is the complete circuit. Okay. Now, each module will take 1 bit and compute the Y, the corresponding Y bit, and then we'll convey the information about the first non-zero to the next module. So we'll have 16 of these smaller modules. Okay, now to write a module for the whole circuit, you say module 2's COM. Module 2's COM. Now we have 2 inputs, each one of 16 bits long, so starting from 15 up to 0, because we know that X is start from X15, X14, down to X0. Same thing for Y, will be the starting from Y15, Y14, down to Y0. Okay, we'll have so many wires, starting from D1, these are wired, D2, up to D16. That's why we have wire 1 to 16. D6, the D. Then we have 1-bit module, 1-bit COM module for each bit of X. That will take bit from X, then the DI, then we generate Y bit and the DO. So the first 1-bit COM we generate D1, second we generate D2 and D3 and so on. Okay. We have to repeat this 16 times, or there is another way to do it using a loop. This is the way to do it using a loop. We have the same inputs and outputs and wire. To do a loop, actually, let me go back here. And we'll do loop for all of these because this is different. This has a DI0 value, but this will start from X1 up to X15, and it will take D1 up to D15, and it will generate Y1 up to Y15, and it will generate also D2 up to D16. So we can have a loop starting from 1 up to 15. And this will be outside of the loop. So we'll have 1-bit COM that deal with X0 and take DI as a 0, 1-bit binary 0. It will generate Y of 0 and the first DO, which is D1. Then we'll do the loop. To do the loop, you have to do the loop to have different, so many calls for a module. We need to use a generate block. We say generate and generate. Then inside this block, we have a for loop. for I equal to 1, I less or equal 15, I equal I plus 1, then begin. Then we put a colon, then we need to have a name for this block, give it any name, then we call the module. One bitcom, we give it a name that will take xi and di, and it will generate yi and di plus 1. Because it will take do from the di from the previous stage and do to the next stage. So if it takes this d1, it will generate d2. If the do is d2, generate d3, and so on. Both of them will work. Let us now see this in action using Quartus. Let me copy first this module because we need it. And we'll go to Quartus. And let me start a new project. We'll start new project, file, new project wizard. I have already an old project, so I close it. I need to select. I will select this directly, but I will have it different name. I will make it maybe ALU, arithmetical logic unit. Use the same name here. Does not exist, created, yes, finish. Okay, it's created. Now I'll start first module, new, Verilog HDL. I will paste the 1-bit comp. I need to name the file using the same name of the module, Control C, save, Control V, save. Also, I'll copy the toolscom module. I'll use this module. File, new, Verilog HDL, Control V. Also, I'll copy the name, Control C. I'll save the module using the same name. I'll save the module, Control V, save. Now I'm ready now to simulate the toolscom circuit. I'll right click here, settings. I'll put the same name here, toolscom, apply, okay. Now we have toolscom here. Now I can double click here, analyze and synthesis to analyze the code and generate the circuit. We'll wait till we get 100%. We have 0 errors. Now we are ready to run the simulation. Go for file, new, University of Grand BWF. Okay. Okay, let me just do 2 examples. I'll go to edit, insert, node or bus, node finder, list. I'm computing the toolscom node of X. And result will be saved into Y. Okay, okay. Now to have only 2 cases, I'll go to edit, set end time. End time will be the number of cases I need to inspect. I only say 2 cases. Then I'll go also send grid size. It will be the same unit microsecond, but it will be 1 microsecond. Now the scale is divided into 2 intervals. I'll start with the first interval. Let me define X. I can define X either in binary or in decimal. Let me divide it in binary. With X. Let me define Y. X for the second interval. Let me make all of these ones. Okay. And before we run the simulation, I have to go to simulation settings. I need to remove this knob opt. Save. So now I'll run the simulation. Save, yes. Save. Okay, now this is the result. It seemed to be correct. Look for this first example. All 4 zeros became as they are. First one zero skipped as is. All the zeros now converted into one. Flipped into one. Same thing here. First one zero is skipped as is. All the remaining ones are flipped. So it seems that we have a correct design. Usually we need to present more examples, but for sake of the demonstration, I did not do that. We are done with the first module. Now we go to the next module. Module is the adder. The adder is not new. We already designed this adder in chapter 4. We'll present the same design. We will use several full adder. We'll use here 16 full adder. Each full adder will deal with a bit from A and bit from B and the carry in. The first carry in will be 0, and each carry out will be injected into the next full adder. Also, we saw the design of full adder in chapter 4 using the truth table. We will not do that here. Just we will present the Verilog module for both the 16-bit adder and full adder. This is the full adder. We presented that already in chapter 4. I will not talk about it. This is the 16-bit adder now. We have 16-bit input A, 15 to 0, same thing B, and we have now the output S, which is also 15 to 0, 16-bit output. Okay. We have so many wires starting from C1 up to C16. So we have wires 16 to 1. For the wire, we can put 1 to 16 or 16 to 1, doesn't make any difference. Then we have, we can use the generate block to use the loop, but I will separate this first from the other because here we have the Cn is 0. So I'll have full adder, we'll add A0, B0 with a Cn0, and it will generate S0 and C1. Then we have a loop starting from A1 up to A16, A1, B1, and up to A1, A16, B16. So we'll have generate and generate for loop, and from 1, I less or equal 15, I equal I plus 1. Then we'll begin, column, we put a name, we call the full adder, we name it any name, so it will take 1 bit AI from A, 1 bit from B, PI, and it will generate, it will take also a carry CI. So the first one will take C1, second one takes C2, and it will generate some SI and CI plus 1, because each one will take CI and generate CI plus 1. Okay. I forgot maybe in the previous generate block, we need to declare the I itself as a var, general variable I. It's not input, not output, not a wire, so we call it var, general variable I semicolon. Then we can also model and can try this in quarters. Let us start with the full adder, Control C, while new, HDL, Control D. Let me copy the name full adder, Control C, save, Control B, save. I'll do the same thing. Usually we need to simulate the full adder, but I will not do that. We did that already in chapter 4. I will simulate the 16-bit adder as a whole. So I will copy now the 16-bit adder module. Control C, while new, Verilog HDL, Control V, I'll copy the name, Control C, save, Control V, save. Now I need to simulate the 16-bit adder. So right click here, settings, Control B, apply, okay. Now I have 16-bit adder. Double click in analysis and synthesis. We wait till we get 0 errors and 100% complete. We have 0 errors. Now we are ready to run simulation. File, new, University of Ground, BWF. Now we are simulating the adder circuit. Let me present two examples. Let's say edit, insert, node or bus, node finder, list. I will add A to B, and it will generate sum. Okay. Let me present two examples. Edit, set end time, make it 2. Set grid size, say grid size always 1. Okay. Let me do this in decimal, sign decimal, or say radix, sign decimal. Let me define XA as, let me make it negative, maybe 12,000 minus 12,000. Let me make B also negative. Okay, minus also 4,000. Let me make them here all positive. Let me make it maybe 1,500. Maybe I'll make this maybe 3,000. Okay. Now before we run the simulation, go to simulation, simulation settings, remove the knob opt. As we said, we need to present more examples, but here for the sake of presentation, we only show 2 examples. Usually better to simulate at least, maybe, now we have so many cases, at least 10 examples. So run the simulation, save, yes, save. Okay. Minus 12,000, minus 4,000, minus 16,000 is correct. 1,500, 3,000, 4,500, it's correct. It seems that our design is correct. Now let us go to the next module, which is the multiplexer. This is a 16-bit multiplexer. We already did that in chapter 4. To remind you that we have this is that we wanted, what we want to design. We want to design this multiplexer. That has input cell. And we are selected between A and B. But both are 16-bit. If cell 0, select A, and to Y, or we call it S here. If cell is 1, we select B. That means, let me just focus on A in S of 0, how to compute S of 0. S of 0, if cell is 0, we select A of 0. Or if cell is 1, we select A of 1. Sorry, B of 0. Or in general, S of I equal cell bar A of I or cell B of I. And this is what we do here. You will have an assign statement for each one of these. For S0, S1, S2, and so on. We can do this by repeating this 16 times or by using the generate block. Okay. This is the one, not here, sorry. This is the one. Okay, and this is the code actually. Either repeating this s of I equals cell bar x of I or cell y of I. Repeat this 16 times, or we use the generate. Here we use the generate. Starting from 0 up to 15. So from I equal to 0, I less or equal 15, or I less than 16, it's the same. I equal I plus 1, then begin, colon, any name. Then we do the assign statement. Assign z of I equal not cell, x of I or cell y of I, semicolon. We need to declare I a gen bar. Okay. And the inputs are a module max 16, input x 15 to 0, y 15 to 0, then the select, then the z 15 to 0. Let us see this in action. I'll copy this module, Control C, new Verilog HDL, Control V. I'll save it using the same name, max 16, Control C, save, Control V, save. Now we need to change this into max 16. Apply, okay. Now analyze and synthesis. We'll wait till we get 0 errors. Have 0 errors. Now go to File, New, Universal Program VWF. And here I'll present two examples. I will keep X and Y constants, but I will change the select. Once I'll make select 0 to select X, then make select 1 to select Y. Edit, insert, node or bus, node finder, list, input X, input Y, then I'll have the select. Okay, select, then the output Z. Okay, so we have two examples. Set end time 2, set grid size 1. Now let me make this constant. I'll make X equal, let me make it signed decimal. Let me make it maybe minus 15. Let me make a Y. Y to be constant also. Let me make it maybe 3000. And here I'll make select 0. Here in this interval make select 2 is 1. So when select is 0 in this interval, Y will be equal to X, which is minus 15. But when select is 1, Y will be equal to Y, which is 3000. Let me change this into decimal also. Radix side. And before we run simulation, we go to simulation settings. We remove this not opt. Save. We run now simulation. Yes. Save. Yes, this is correct. Now, since cell here in this area is equal to 0, so it selects the 15. Here is equal to 1, selects to 3000, and we can see this clearly if you click here to snap grid, and we pull this bar. So in this interval, we have x minus 15, y 3000, but cell is 0, so x is selected. But in this interval now, same x and y, but cell is 1, so y is selected. Close this. Final module is the overflow checker now. Now to check for overflow, let me remind you that we are computing this operation. This plus this. We said if for the overflow to happen, these must have the same sign, either positive or negative. And they should have different sign than the sign of y. So let me name now the sign of this term as S1. So S1 will be the sign of this term. S1. And S2 the sign of second term. And SY is the sign of y. And let us compute the sign of this term, sign of this term. The sign of this term is the XOR between the SA value and the sign of A. The sign of A is A15. Sign of B is B15. Why the XOR? Because if both are different, and if A is 0 and A15 is 1, or this is 1, this is 0, they are different. So this is positive, this is negative, sign will be negative. Because positive negative is negative and negative positive is negative. And this is the XOR. They are the same, 0, 0 or 1, 1. That means positive, positive will be positive, negative, negative will be positive. And this is the XOR operation actually. So operation between SA and A15. So this is this one. Same thing for S2, it will be XOR between SB and B15. Now, for the overflow to happen, S1 must be equal to S2. So either both 1 or both zeros. That's why we have bar. And they are different than SY. So if they are 1, SY must be 0. If they are zeros, Y must be 1. And this is the overall expression for the overflow. Now we can write a module for the overflow. We could have used this directly inside the bigger circuit, but I prefer to build a separate module for this to make it more readable. So let us build a module for the overflow, but we will not simulate it here. We'll keep it for you, but it's very simple. Let us see this here. We have module overflow check, input SA, input SP, input sign A, input sign B, input sign Y, output overflow. And we define S1 as the sign for this term, which is SAA. S1, this is the sign of this term, and S2 is the sign of SPB. So we have a sign S1 equal SA XOR sign A, S2 equal SB XOR sign B, as we mentioned earlier. Then we have the overflow expression. S1 and S2 and it not sign Y, or not S1, S2 and sign Y. Let us check this. We'll not check it, sorry. We'll not check this. We'll keep it for you and you can do it yourself. We are sure about our design, but usually it's better in that design problem you have to model and simulate everything, but I will not do that here. But we will now write a module for the whole circuit. This is the module for the whole circuit. Okay, this is our circuit, and this is the overflow module. This is the complete circuit. So these are the inputs. Let us start to define inputs and the outputs. Inputs are A, B, SA, SB. And the outputs are Y and the overflow. Okay, that's why we have module at sub input 15 to 0A, 15 to 0B, input is A, input is B, output 15 to 0Y, then output overflow. And it's very important to define these wires. We have here W, this wire, this is 16-bit, because we have this input 16-bit. Same thing for W2, this is 16-bit. This is W3, also 16-bit. And this is also W4, 16-bit. So we have 4 wires. That's why we have wire 15 to 0, W1, W2, W3, W4. Okay. Okay, now we are ready to complete the module. Actually, we don't need this. Sorry, I wrote this, but then I discovered I don't need it. Let me start now. We can now describe our circuit starting from anywhere we want. We can start from the checker, we can start from the adder, or anywhere. I'll start from here, start from this two's complement. I would say we need a two's complement module. So you have two's com. I call it TCM0. So this is TCM0. That will have an input A and output W1. Input A, output W1, semicolon. Then the max. We have a max 16. Max 16. I call it max 1. Max 0, sorry, it's strange name, but it's max 0. This is max 0. Should be max 0, but this is what I did. The two inputs A and W1. So A, W1, then the selector is A, then the output W3, semicolon. I'll do the same thing here for the B. I will have two's com. I call it TCM1. This is TCM1. Input is B, output is W2. So input is B, output W2. Then I have multiplexer. The inputs to the multiplexer are B, W2, SP. We call this max 1. This is max 1. So the inputs B, W2, SP, and the output is W4. Then we have the 16-bit adder that will add W3 to W4 and it will generate Y. 16-bit adder, call it SPA. 16-bit adder, SPA. Add W3 to W4 and it will generate Y. Then finally we have the overflow checker. Overflow check. I named A, O, B, C. These are the inputs. SA, SB. A15, which is the sign of A. Then B15, which is the sign of B. Then we have Y15, which is the sign of Y. Then we have the output, which is overflow. Okay, we could have named this sign A, sign B, sign Y, and then we use the wire. Say wire, sign A, sign B, sign Y. Then we said a sign A equal A15, sign B equal B15, sign Y equal Y15, but I didn't do that. I don't need to do that because we already, when we defined the module, we defined this input as sign A and sign B. Okay. Now we're ready to see the simulation results. Let's go to Squartus. Let me copy this. Control C. Then I'll go to Quartus. File, new, Verilog HDL. Control V. We need it at sub. I'll copy this at sub. Control C. Save. Control V. Also change this name into add sub settings. Control V. Apply. Okay. Now double click analysis and synthesis. Let us wait till we have 0 errors. Okay, they have an over. I think we did not copy the overflow. Sorry, that's why. We need also to have a module for the overflow. New Verilog HDL. We need also to copy this, Control C, Control V. We'll name it the same name, Control C, Control V, save. Now we'll run it again. Okay, zeros. Now we can do the simulation. New, let's run PWF. Okay, let us present two cases also. One case or three cases. One case when we have the overflow, and two cases without overflow. Let me insert node or bus, node finder, list. I'll add A, and I have the sign for A. Let me I'll rearrange them later. It's B, I need B. I need also SA and SP both. I need also the Y and the overflow. Overflow and the Y. Okay. Oh, sorry. Redo it. Sorry for that. Insert node or bus, node finder, list A, B, SP, Y, and then overflow. Okay. Let me rearrange now. Let SA in front of A, SP in front of B, then I have Y and the overflow. I will say we present three cases. Edit, set end time, make it 3. Then set grid size, we'll make it 1 microsecond. Okay, let me start with the first case. Let me add now, let me make SA, maybe make it negative. Make A, maybe, let me sign, let's make it minus 15,000. Okay, let me make SB positive and make SB maybe 3,000. Okay. So in this case, let us see what we should expect as a result. We have now SA is positive, is 1, sorry, SA is 1, and A equal minus 15,000. SP is 0, which is positive, and B is equal 3,000. So we have minus 15,000, it will be 15,000. Then plus 3,000 should be 18,000. Okay, let's consider the second case. Maybe here we'll keep SA positive. Let me make A equal maybe minus 20,000 and make SP negative now. And let me make P maybe 30,000. No, not 30,000, 12,000 or 10,000. 10,000. Okay. So now we have here SA is 0, which is positive, and A is minus 20,000. B SP, sorry, SB is negative, which is 1, and B equal 10,000. So we have plus minus 20,000, so minus 20,000, then minus 10,000 will be minus 30,000. Okay. Last case. Now, if you remember that we have now 16-bit adder, but we use sign number, so half of it. So the combination, number of combinations, we have 2 to the power 16 combinations. But half of it is positive, so which is 2 to the power 15. Half of it is negative. 2 to the power 15 is 32,768. So for the positive, we have one of them is equal to 0, and we don't have negative into 0. So the number x can be between greater than minus 32,768 and less or equal 32,767. This is the result we can represent. So let us now present an overflow case. Let us make it -1. Okay, we need to generate an addition that will exceed this value as a magnitude. Let us do that here. Let me make SA negative, and I will make A is positive. Let me make it 30,000. Okay. And let me make SB positive, but the B is negative. Let me make it minus 2,769. And just one more than this. Yeah, this is this will be the end result will be 32,769 instead of 68. Let us see this here now. Now what we have here, we have SA equal 1, which is negative, A equal 30,000. Then we have SP 0, which is positive, but the B is minus 2,769. So we'll have minus 30,000, then plus minus 2,769, which will be minus 32,769, which is an overflow, because this is the maximum negative value we can get. Which one? Which this? What is that? This one. And this will exceed it by 1. The negative side. Let us see. And here we'll get correct answer, no overflow, but here we'll get over. Let us see that. Let us, before we run simulation, go to simulation settings, nav opt, save, then we run the simulation. Yes, save. Okay, let us now make this decimal and sign periodics, sign decimal. This is, we expected 18,000, which is correct. No overflow. Overflow is 0. Expected minus 30,000, which is correct. But here we expected minus 32,769. But we did not get the correct answer. We get positive answer. That's why we have an overflow. See here, the overflow is 1. And we are expecting this actually. So it seems that design is correct, even in computing or detecting the overflow. Okay, this is the end of our design. But before we end our session, one more thing we need to mention, which we asked you to do in your design. Let us see that. Let us go to the design of the tools component. This is the tools component design. Okay. If you remember, we in the design probably will ask you to select one module, one of these module, and to talk about two different alternatives to design it. And we'll do a similar thing here for the tools component module. We'll not do a complete different alternative, but it will be different in some aspects. One way to design this module, instead of having this input, and we can remove this. I'm sorry, not I'll remove the output, sorry. I'll keep this input, and I'll remove this input, so we'll not have this output. We'll remove the output, sorry. And I can have the module only with the DI input, without the DI. Okay, but then how to compute the DI? Very simple. For this one, it will be the value of x0. If x0 is 1, DI will be 1. For this input now here, so now we don't have this one, it will be the OR. So the OR between the x1 and the x0. Same thing for this one, will be the OR of x2, because if either one of them is 1, that means the first one 0 already appeared. So this is a slightly different design. Now, if you compare it based on scalability, and the main design is more scalable, because now if you have a long input, assume that you have maybe 1024 bit tools component module, and we need an OR gate of such huge inputs, because I need to OR all the X's together to provide the DI value. So this is not scalable. Also will be more complex compared to the main design. That's why we selected this design, and we prefer design for the other design. And you will do a similar thing in your project. And you select one of the modules, and you will do, we will briefly talk about two different approaches to design the module. Then we'll select one of them, and then you will detail the one that you selected. And I think that's it for this session. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.